All right, everyone. So in this video, we're going to be talking about electron hybridization, and we'll also get into molecular orbitals, okay? Not atomic orbitals, but molecular orbitals. So first of all, hybridization. What does it mean when electron orbitals are hybridized? It essentially means that when you have one atom and it's about to get bonded with another atom or a set of atoms, the bond that it makes, it creates by fusing its orbitals together to make a new kind of mutant or hybridized new orbital. So if you remember from our first video, we said the only orbitals that we're worried about were the S's and the P's, right? And the S orbitals looked like spheres. They were spheres. And all the P orbitals, there were 3 of them per energy level, and they all look like dumbbells. So one was in the X direction like that, one was in the Y direction like that, and one was in the Z direction, so coming out at you and then going away from you like that. But basically all dumbbell shaped. Well, the thing is, when atoms bond to other atoms, they don't just take one of these orbitals, electron orbitals, and have it fuse with the orbital of the other atom. What they do is fuse their own orbitals together to make a new orbital. So an atom might take its s orbital and one of its p orbitals and create a new orbital that we would call an sp. And that sp orbital will have partial s character and partial p character. So it'll look like a kind of fusion between the two. So it'll be, I can never draw them properly. You can probably just Google them. So that would be the P, and then that would be the S. So the P has a little bit of S character, and the S has a little bit of P character. If the atom were to combine one of its S's, and it only has the one S per energy level, right? With 2 P's, then you would have something that has a little bit of S character and a lot of P character, so maybe like a little bit longer. So this would be an sp hybridized orbital, brand new orbital. This would be an sp2 because we had 2 p's that we used along with 1 s, and so on. The rule that atoms follow when it comes to hybridization is atoms know exactly how many other atoms that they're bonding to. So if we had, for example, carbon dioxide, that's CO2, right? And we were looking at the hybridization of the carbon atom in the middle. That carbon atom knows that it's bonded to 2 things, one oxygen and another oxygen. So because it's bonded to 2 things, and the carbon has in its armory, if you will, or in its closet, 1 s and 3 p's to choose from to make a hybridized orbital, it's going to choose first one of the s's. You always start with the s and then one of the p's. So it's going to make an sp. Its 2 other orbitals, the 2 other p's, will just remain empty. They won't have any electrons in them. Or they won't participate in bonding, I should say. So because the carbon knew that it was being bonded to 2 other atoms, one oxygen over here and another one over here, it said that it's going to create its bond by taking 2 orbitals, one s and one p, because it's got a bond to 2 things, fuse them together to make an sp, And that's how the one of the bonds that are made, let's say this top one right here, this is double bonded, right? So one of these bonds are going to be an sp bond. So I know this sounds a little bit confusing, but let me show you some more examples. Let's say we have carbon and it's bonded to 4 methyls or 4 chlorides. Let's just say chloride. Okay. So this carbon knows that it's bonded to 4 different things, 4 different chlorides. And we can even replace one, and I'll just put a methyl. Doesn't really matter what atom is attached to it, or hydrogen. It doesn't matter what atom is attached to it, but the carbon knows that it's attached to 4 different things. 1, 2, 3, 4. And it has an S and 3 Ps to choose from. Because it's being bound to 4 different things, it's going to have to choose all 4 of its orbital options. So it's going to have to select one S, one P, another P, and another P, because that's 4 things. 1, 2, 3, 4. So if you have one S and you're taking 3 Ps and you're shoving them all together, like mixing them together to make a brand new hybridized orbital, you've made an sp3 orbital. You had the one S and now you have 3 Ps. So each of these bonds right here, these are all sp3 bonds. Okay, let's look at another example. Let's look at and let's look at this carbon right here. So what are the things that that carbon is bonded to? Well, it's bonded to 3 hydrogens. It's a methyl group, but it's also bonded to that carbon right there, the carbonyl carbon, right? So that carbon is bonded to 4 things, 3 hydrogens and 1 carbon. So it's going to require the help of all 4 of the orbitals that comprise it. So it's going to need its 1s, and it's going to need the 3 Ps, the Px, the Py, and the Pz. And it's going to have to hybridize them all together and make a brand new hybridized mutant orbital that we call the sp3 that it uses to bond with all of its neighbors. Now let's look at this carbon right here, the carbonyl carbon. What is it bonded to? It's bonded to an oxygen and a methyl and another methyl, right? Now it's double bonded to the oxygen, but that doesn't matter. All that matters is how many things are attached to our atom of interest. So even though there's a double bond here, all we're saying is that that carbon has 3 things attached to it. So it's going to need, out of its closet or cabinet or whatever, which is filled with 1s and 3p orbitals, only 3 of those orbitals to hybridize together. It's bonded to 3 things, so it needs only 3 orbitals. So it's going to take an S. You always have to start with an S, and 2 Ps, because that's 3 things. So it'll be sp2. I'm going to erase this. We're going to stay on this one, on this example. So hopefully now you're able to see pretty clearly that this carbon was sp3, this carbon was sp2, this carbon was sp3. But what about the oxygen? What about that that oxygen? Well, we know that that oxygen has two lone pairs of electrons, right? I just didn't draw them in, but you know they were there. So the other rule for hybridization is if you have a lone pair of electrons, your atom, even though it owns its own lone pair, they belong to it, thinks that that lone pair is like another atom. So that oxygen thinks that its lone pair right there is like another hydrogen sticking off of it or something. So this oxygen thinks it's bonded to three different things. It thinks that it's bonded to this carbon and that it's bonded to something else over here and something else over there. So the oxygen feels that it's bonded to three different things. And it has an S and three Ps to select from. So because it thinks it's bonded to three different things, it's going to pick three different orbitals, one S and two Ps. So the oxygen is going to be sp2. Let's do another example. Ammonia, Nh3. So there's Nh3, but we know that nitrogen is a group 5 element, and its valence has 5 electrons. So here's 1, 2, 3 that it's using in bonding, but it's got that lone pair, 4, 5. So what does this nitrogen think? The nitrogen thinks that it's bonded to one thing, two things, three things, and it thinks its lone pair is like another atom, so 4 things. So that nitrogen in its little nitrogen brain thinks it's bonded to 4 things, so it is going to need to select 4 orbitals to kind of squish together to make a new hybridized orbital. So it'll need its S, then one P, another P, and another P. It'll squish them all together for an sp3 orbital, brand new orbital. Let's try another one. So hopefully you're getting the hang of this now. What if we had OF2? Oxygen with 2 fluorines attached to it. So there's our O, there's an F, and there's an F. And we're chemistry pros now, so I don't even have to draw anything in, but you know that there's 2 lone pairs right here. So this oxygen, in its little oxygen brain, thinks that it's attached to one atom, this fluorine, another one, and it thinks its lone pairs are 2 other atoms. So this oxygen thinks that it's attached to 4 things. So it's going to need 4 orbitals, one S, one P, another P, and another P. So it's going to be hybridized sp3. Even though it only has 2 atoms bonded to it, it's still hybridized sp3. So always take note of how many lone pairs you have. Let's do a couple of more examples. What if we had this? What would the hybridization be of that carbon right there? Well, that carbon is bonded to this oxygen, but it's also bonded to that carbon in the ring and that carbon in the ring. It looks like this, right? So our pink carbon is bonded to 3 different things. If it's bonded to 3 different things, it must be an sp2. Let's try this. What would the hybridization be of that carbon right there? So hopefully you said sp, because this molecule looks like this. We have an oxygen, double bonded to a carbon. Then this carbon is bonded to that carbon, double bonded. That carbon has an H on it, and it's also bonded to that methyl. But we were only interested in this carbon right here. It's bonded to one thing, this oxygen, and another thing, that carbon. And there's no lone pairs. Carbon is a group 4 element. Its valence shell has 4 electrons, and here they are, 1, 2, 3, and 4. So there's no extra lone pairs anywhere. So the only thing we're interested in is not the lone pairs in this case, but just the atoms attached to it, which are this oxygen and that carbon. So it only has 2 buddies that it's connecting with, so it only needs 2 of its 4 orbitals. You got to start with the S, so it'll take the S and the P, 1 S and 1 P. So it'll be sp hybridized. Let's do one last one. I'll give you a crazy one. You're not likely to see this for a couple of weeks. But that's a triple bond. So we've looked at double bonds, now that's a triple bond. So I'll help you out a little bit here. This looks like this, right? So are there any H's off of these carbons right here? So hopefully you were able to identify that no, there are no H's, because the carbon, the 2 carbons that are participating in the double bond already have all 4 of their electrons participating in bonds. So they don't have like a 5th electron that's hooked up to a hydrogen that's just invisible. So this carbon right here has 1 of its valence electrons there, a 2nd one, 3rd one, and a 4th one. Same with this carbon. 1, 2, 3, and 4, all 4 of its valence electrons are participating in bonding. So what would the hybridization be of this carbon right there? So it's only bonded to 2 things, this carbon and that carbon. So that's an sp. What would the hybridization be of this carbon right here? So hopefully you said sp3, because it's bonded to 4 things, 3 hydrogens and 1 carbon. So this is an sp atom, and that's an sp3 atom. Okay, now let's get into molecular geometries or molecular orbitals, okay? So these are essentially geometries that molecules, that you can find molecules in based on how many atoms are attached to a central atom and how many lone pairs that central atom has. And you only need to know 5 in this class. The first one you have to be aware of, I mean, there's more than 5, but we only have to know 5. The first one is linear. A linear geometry or configuration is when you have a central atom, and we'll just call that A. So A is probably like a carbon, let's say, and it's bonded in a straight line to some other carbon, X. Doesn't have to be a halogen. X just means any other atom, and another atom on its other side, X. And the angle between the two substituents that are bonded to that central A carbon is 180 degrees. So we say that the two substituents are 180 degrees from one another, separated from one another, or oriented from one another. So that's a linear geometry. The second geometry we should be aware of is trigonal planar. Trigonal planar is when you have three atoms bonded to a central atom, but they're all in a plane. So if you were to take a sheet of paper and just draw this out, right, two-dimensionally, all of the atoms that are on the sheet of paper would all be in one plane, in that two-dimensional plane. So that you have three atoms bonded to a central atom, trigonal, but they're all in one plane, so trigonal planar. And the bond angles between the atoms attached to the central atom is 120 degrees. The third geometry we should be aware of is tetrahedral. Tetrahedral is when you have four atoms attached to a central atom. So there's our central atom. Here's one atom attached to it. Here's another one. Here's one coming out at you, out of your computer screen, and one going away from you. And the bond angles between the substituent groups attached to the central atom is 1095. And this is a number I would absolutely memorize, 1095. The fourth geometry we should know is called bent. A bent geometry is like a linear geometry, but the two atoms off of the central atom are like pointed down. They're bending towards one another. And the reason for that is because our central atom has a lone pair of electron, or a couple of lone pairs of electrons that are unbonded. Electrons are negatively charged, right? And so when they're sitting there in their orbitals, they're repelling themselves and other atoms away from one another. It's like having two magnets that are the same charge. They're not going to be able to stick. They're going to push each other away. So the X's might want to be in a linear line, just like we were up here in our linear configuration, 180 degrees apart. But A's two lone pairs of electrons are pushing them further away from one another. And so the angle that we have between our two substituents is going to be a lot less than 180 degrees. In fact, it's going to be 105 degrees. And the last one we should be aware of is trigonal pyramidal. And trigonal pyramidal is kind of like tetrahedral, except in this case, you do have three atoms attached to a central atom, but not a fourth one. The fourth one is just a lone pair of electrons that it has. So those pairs are also pushing the X's away from it and more towards one another. And so the bond angles that we have between the X's, between the substituents, are going to be a little bit less than 109.5. So they're 107 degrees. Okay. So let's go ahead and give some examples. So a linear molecule would be carbon dioxide. The central carbon does not have any lone pairs of electrons, right? Because all of its valence shell electrons are being used up in bonding. Here's one, here's another, a second, third, and fourth. So it's going to be linear. How about trigonal planar? Trigonal planar can be something like boron with 3 fluorines attached to it. Boron is a group 3 element, so it has only 3 electrons in its valence shell. So, oops, so there's one, there's the second one, and there's a third one. So there's no extra lone pairs of electrons anywhere. So that would be trigonal planar. Tetrahedral is just our old friend methane, or anything, any 4 atoms that are bonded to carbon, to a central carbon. No extra lone pairs left over. I put an H or C. I could have left it as a C. No extra lone pairs left over on that central carbon. How about bent? What's a good example of that? Maybe something like this. Something with a ketone functionality. Well, that's not a ketone, sorry. I believe that's an ether. We know that oxygen has 2 lone pairs of electrons that I didn't initially draw in, but you know they were there. So that's not going to have a linear configuration. It's going to have a bent configuration. And an example of trigonal pyramidal would be something like ammonia. So you would have a central nitrogen atom, then you would have 3 hydrogens, but we know nitrogen is group 5, so 1, 2, 3, and a lone pair would make 4 and 5. So it would not be a tetrahedral, but it would be a trigonal planar. So let's do a couple of quick examples where we put everything together. So I'll go ahead and erase all this. So let's look at something like this. So what would you say the hybridization is of that pink carbon right there? The hybridization. So I hope you said that it was sp2, because we know that that carbon is bonded to one carbon, one thing up here, this carbon over here, a second thing, and this is a line bond formula or structure, so we didn't show that there was a hydrogen right there, right? Because the carbon has to have 4 bonds. It's tetravalent. So here's 1, 2, this double bond, 3, and the hydrogen we didn't show, but that was the fourth bond. So sorry, I meant to say sp3. I made a mistake. Wrote it down wrong in my notes, so that should have been sp3. And so if we had to guess what kind of geometry, its molecular orbital geometry it has, what would we say? Well, it's bonded to 3 different things, right? It's bonded to those other 2 pink carbons and the hydrogen. So we have a central atom that's bonded to 3 different, essentially 3 different things. So this would be a trigonal planar geometry. How about this nitrogen right here? What is its hybridization? Well, I hope you were able to see that that nitrogen actually looks like this. It has a hydrogen on it, right? Then it's bonded to this carbon right here, which is that, and that carbon right there, which is like that. But it also has that lone pair, because it's a group 5. So here's 1 of its valence shell electrons, 2, 3, 4, and 5. So how many things are bonded? How many things does the nitrogen think it's bonded to? It thinks it's bonded to this carbon, 1, 2, that hydrogen 3, and then that 4. So that nitrogen is going to be an sp3. Now, if it's bonded to 3 atoms and it has 1 lone pair, 3 atoms and 1 lone pair, then its geometry is going to be trigonal pyramidal. How about this carbon right here? Right there. What is its hybridization? Well, I hope you were able to see that it is bonded to this carbon here, this nitrogen here, and it has 2 other hydrogens that we don't show in the line bond structure. So it's bonded to 4 different things. So it's going to be an sp3, and it's bonded to 4 different atoms, and it has no lone pair of electrons. So 4 different atoms and no lone pairs means it's a tetrahedral. Okay, so we're kind of putting everything together. So let's close out this video here, and we'll move on to the next topic in just a bit.